The berries look harmless. They hang in clusters beneath broad leaves, shining in the sunlight after a passing rain. Nearby, a stream cuts through a patchwork of forest and grassland. Insects drift through warm air. Birds call from the trees. Everything appears alive, abundant, inviting. Yet somewhere in this landscape, perhaps only a few steps away, grows another plant that looks almost identical. Its fruit is bitter with chemicals evolved over millions of years to discourage hungry mouths. A handful of those berries may bring sickness. A larger handful may bring death. For most of human history, there are no labels, no field guides, no written warnings, and no experts waiting nearby with answers. There is only the land and the countless dangers hidden within it. This is the world inherited by the earliest humans. Before we go deeper, take a moment to like the video and subscribe if this is the kind of history and mystery you enjoy. The challenge facing prehistoric people is difficult to imagine from a modern perspective. Today, a trip to a grocery store offers food that has already survived generations of testing, farming, regulation, and cultural selection. Most dangerous species have been filtered out long before they reach a plate, but for early humans, every landscape is filled with uncertainty. Every unfamiliar root, seed, mushroom, shellfish, insect, or animal presents a question that cannot be ignored. Can it be eaten? The answer matters because hunger never stops asking. The prehistoric world is not a giant buffet waiting to be explored. It is a battlefield of biological deception. Plants do not want to be eaten. Fungi do not announce which varieties contain lethal toxins. Water that appears crystal clear may carry invisible dangers. Even successful hunts can lead to sickness if meat spoils or parasites survive inside it. Natural selection has spent hundreds of millions of years equipping living things with defenses. Thorns are obvious, poison is not. Many plants manufacture powerful chemical compounds. Some disrupt digestion, others attack the nervous system. Some interfere with the heart, others damage the liver over time. Modern science continues to discover thousands of these substances, many of which evolved specifically to discourage herbivores and omnivores. What survives in the archaeological and biological records suggests that early humans entered an environment already saturated with these defenses. The danger extended far beyond plants. Certain fish contain toxins. Some shellfish become poisonous under specific environmental conditions. Reptiles, amphibians, insects, and even mammals can carry substances harmful to human bodies. Spoilage introduces yet another layer of risk. A meal that is safe one day may become deadly the next. Yet despite all of this, humans survive. Not only do they survive, they spread across continents, they cross deserts, forests, mountains, coastlines, and frozen regions. They adapt to ecosystems so different that they sometimes appear almost unrelated. The mystery is not simply how they found food. The mystery is how they managed to identify safe food, often enough to avoid disappearing entirely. The answer begins with the simple reality. The first humans almost certainly made mistakes. Many mistakes. The archaeological record rarely preserves individual tragedies. Bones may survive, but the precise meal that caused an illness thousands of years ago is usually lost forever. Still, anthropologists and evolutionary biologists agree on one point. Knowledge about edible foods could not have appeared magically. It had to be acquired. Somewhere in the distant past, people ate the wrong things. Some became sick and recovered. Others probably never recovered at all. This process sounds brutal because it was... Imagine a small group moving through unfamiliar territory during a seasonal migration. Familiar food sources have become scarce. New plants appear along the edge of a valley. Some individuals sample them cautiously. Perhaps nothing happens. Perhaps mild discomfort follows. Perhaps hours later someone develops violent symptoms. The group watches. Lessons are learned. Memory forms around the event. Over countless generations, experiences like these accumulate. The knowledge itself becomes a survival tool. One of humanity's greatest advantages is not sharper teeth, stronger claws, or greater speed. It is the ability to remember and share information. A dangerous berry discovered by one individual does not have to claim every member of the group. The lesson can spread. Parents can teach children. Elders can warn younger generations. Communities can transform isolated accidents into collective knowledge. This may seem obvious now, but it represents a profound evolutionary advantage. Many animals learn from experience. Humans build traditions. That distinction changes everything. As knowledge accumulates, landscapes begin to transform. The same forest that once appeared confusing and threatening gradually becomes a map of opportunities and hazards. Certain trees produce valuable nuts. Particular roots are edible only during specific seasons. Some mushrooms are avoided entirely. Others become prized resources. Dangerous areas acquire stories. Safe gathering grounds acquire familiarity. The land itself becomes readable. Yet reading nature is never easy. One reason is that poisonous foods are not always obvious. Some toxic plants advertise their defenses with bitterness or unpleasant odors. Others do not. Some look almost identical to harmless relatives. Even today, experienced foragers occasionally make fatal mistakes. Scholars still debate exactly how early humans balanced caution against necessity in different environments. But the evidence remains incomplete, because most of these decisions leave few traces behind. What survives instead are clues. Archaeological sites reveal grinding stones stained by ancient plant residues. Fossilized teeth preserve microscopic evidence of consumed foods. Ancient cooking hearths contain fragments of seeds, roots, shells, and bones. Together, these fragments suggest a long story of experimentation, adaptation, and growing sophistication. Perhaps the most surprising detail is that prehistoric diets were often far more diverse than many people imagine. Rather than relying on a narrow range of foods, many hunter-gatherer groups exploited dozens or even hundreds of different species. This diversity reduced risk. If one food source failed or proved dangerous, alternatives existed. But diversity also created new challenges. The more options available, the more knowledge required. A person living in a tropical forest might need to recognize hundreds of useful plants. A coastal community would need expertise about fish, shellfish, tides, seasonal blooms, and changing conditions. Arctic populations face different dangers entirely. Everywhere humans traveled, the list of potential foods expanded, along with the list of possible mistakes. This constant tension shaped human history long before cities, kingdoms, or agriculture appeared. Every meal carried information. Every successful meal reinforced a lesson. Every failure carried consequences. The familiar human story of exploration and survival is often told through migrations, hunts, tools, and climate change. Yet beneath all of those events lies a quieter struggle. Before humans could build monuments, sail oceans, domesticate crops, or create civilizations, they first had to solve a simpler problem. They had to learn what would not kill them. And that lesson was written across countless generations, in forests, grasslands, deserts, rivers, coastlines, and mountains. It was learned through observation, memory, caution, hunger, and sometimes tragedy. The world offered no instructions. The environment provided no guarantees. Survival depended on transforming uncertainty into knowledge one meal at a time. The first lessons about food are unlikely to have been taught around a fire. They were probably taught by consequences. Long before written language, before villages, before agriculture, and perhaps even before fully modern humans appeared, information about safe and dangerous foods had to emerge from direct encounters with the natural world. Every generation inherited some knowledge from those who came before, but that knowledge had to originate somewhere. At some point in the distant past, someone became the first individual to bite into a particular fruit, chew a certain leaf, dig up an unfamiliar root, or taste a mushroom never eaten before by their group. What happened next helped determine whether that food entered humanity's menu or remained permanently avoided. The process was almost certainly uneven and imperfect. No single explanation fully accounts for how prehistoric humans expanded their understanding of edible resources across thousands of environments. Different groups likely developed different strategies. Some knowledge may have been discovered repeatedly by unrelated populations separated by continents and millennia. Other discoveries may have spread through contact between neighboring communities. What remains clear is that the acquisition of food knowledge came with risks. In modern medicine, researchers carefully test substances under controlled conditions. In prehistory, the environment conducted its own experiments, often without mercy. A toxic plant does not announce itself before consumption. Symptoms arrive only afterward. Sometimes the effects appear within minutes. Sometimes they emerge hours later. In other cases, harmful compounds accumulate slowly, making the connection between cause and effect difficult to recognize. This delay presents a problem. If someone becomes sick immediately after eating a particular berry, the lesson is straightforward. If symptoms appear a day later, after several meals and countless activities, identifying the culprit becomes far more complicated. Early humans faced these challenges without laboratories, chemistry, or biological theory. They had only observation. Yet observation can be remarkably powerful. Anthropologists studying recent hunter-gatherer societies have noted the extraordinary attention many groups pay to environmental details. Small changes in plant appearance, animal behavior, seasonal timing, and landscape conditions are often noticed and remembered. Such skills likely have deep evolutionary roots. For prehistoric humans, survival rewards careful observers. A person who notices that certain berries consistently cause stomach pain gains valuable information. A family that remembers which routes become safer after winter frosts gains an advantage. A community that recognizes patterns between specific foods and specific illnesses becomes more resilient. Knowledge accumulates slowly, but once established, it can spread. The first fatal experiments may therefore have served a larger purpose, though not intentionally. Individual suffering could become collective wisdom. This idea sounds harsh, but nature rarely offers gentle pathways to adaptation. Modern humans sometimes imagine ancient people as reckless because they lacked scientific knowledge. In reality, the opposite may often have been true. When uncertainty carries life or death consequences, caution becomes a valuable survival trait. Evidence from ethnographic studies suggests that many traditional societies approach unfamiliar foods carefully. Small quantities are tested first. Reactions are monitored. Preparation methods are refined. Such practices may reflect habits developed over countless generations of experience. The image of prehistoric people randomly eating everything they encounter is almost certainly inaccurate. Hunger encourages experimentation, but survival favors restraint. This balance between curiosity and caution likely shaped much of early human behavior. Imagine a small band entering a new region after seasonal migrations. Familiar food sources are scarce. New plants dominate the landscape. The group cannot ignore these resources indefinitely. At some point, someone must investigate. Perhaps they begin with tiny amounts. Perhaps they watch local animals. Perhaps they compare unfamiliar species to known ones. Perhaps they rely on smell, texture, or taste. None of these methods guarantees safety. Many poisonous foods have been consumed by animals that tolerate toxins. Humans cannot. Some toxic plants smell pleasant. Others taste surprisingly mild. Nature offers clues, but rarely certainty. The first encounters with dangerous foods therefore probably produced a wide range of outcomes. Some individuals experience mild discomfort, others endure severe illness. A few foods prove harmless despite initial suspicion. Certain resources reveal unexpected benefits. Over time, distinctions emerge between dangerous, useful, and valuable species. What begins as uncertainty gradually transforms into knowledge. Archaeology occasionally offers glimpses of this process. At ancient sites across Africa, Europe, Asia, and Australia, researchers find evidence of surprisingly broad diets. Residues trapped in stone tools reveal the processing of seeds, nuts, tubers, and wild grains. Microscopic plant remains embedded in dental calculus show that prehistoric people consumed species once thought too difficult or risky to exploit. These discoveries suggest something important. Early humans were not merely reacting to their environments, they were actively investigating them. They experimented, not in the modern scientific sense, but in a practical survival sense. They tested possibilities, they refined techniques, they expanded dietary boundaries. Some experiments likely failed. Others transformed entire communities. One lesser-known detail emerges from studies of bitter taste perception. Humans possess specialized taste receptors capable of detecting many potentially harmful compounds. Scientists believe these receptors evolved partly as protection against plant toxins. Bitter flavors often trigger caution because, throughout evolutionary history, bitterness frequently signaled danger. Yet the relationship is complicated. Many nutritious foods are also bitter. Certain medicinal plants are bitter. Some toxins are not bitter at all. As a result, taste functions as a guide rather than a guarantee. The same pattern appears throughout prehistoric food gathering. No single clue provides certainty. Survival depends on combining many forms of information: visual appearance, smell, taste, season, location, past experience, group memory, observed consequences. Together, these pieces form an increasingly sophisticated system of decision-making. Over generations, as communities begin developing mental maps of risk, certain foods become trusted staples. Others are reserved for emergencies. Some require elaborate preparation before consumption. A few are avoided entirely. The process resembles the construction of an invisible library. Unlike modern libraries, however, this one exists entirely in human memory. Every safe meal adds a page. Every dangerous encounter adds another. The library grows generation after generation. Its contents become essential for survival. Without it, each generation would be forced to start over, repeating the same deadly mistakes. With it, knowledge accumulates faster than biological evolution alone could ever manage. This ability to preserve lessons may represent one of humanity's most powerful adaptations. Sharp claws evolve slowly. Culture evolves rapidly. A poisonous plant capable of killing an individual can be neutralized by information shared across an entire group. The toxin remains dangerous, but the community becomes safer because knowledge spreads faster than genes. Some scholars argue that this capacity for cultural learning helped humans expand into environments that would otherwise have been impossible to occupy. The evidence remains incomplete, but the pattern appears repeatedly throughout prehistory. Wherever humans travel, they eventually develop detailed knowledge of local resources. Knowledge becomes an ecological tool, and sometimes that tool matters more than physical strength. By the time anatomically modern humans begin spreading across vast regions of Africa and beyond, countless generations of observation have already transformed the relationship between people and food. The world remains dangerous, but it's no longer entirely mysterious. Lessons learned through sickness, caution, success, and failure have started to illuminate the landscape. Yet another challenge remains. Knowing that something is dangerous is only part of survival. The next step is learning how to recognize danger before it strikes. And in a world where every valley, forest, shoreline, and riverbank hides new uncertainties, that skill becomes one of the most valuable forms of knowledge any human can possess. Once humans begin building a library of experience, a new problem emerges. Memory can preserve lessons from the past, but it cannot eliminate uncertainty from the future. Every journey into unfamiliar territory introduces new plants, new animals, and new risks. A berry that is safe in one valley may have a dangerous relative in another. A mushroom gathered successfully for years may suddenly become deadly if mistaken for a similar species. Even among familiar foods, seasonal changes can alter chemical composition, making some resources more toxic at certain times of the year. The prehistoric world remains full of traps. To survive, humans must learn how to recognize warning signs before they take a bite. This effort transforms observation into one of the most important survival skills ever developed. Imagine standing at the edge of a forest 40,000 years ago. You possess no scientific understanding of alkaloids, glycosides, oxalates, or neurotoxins. You've never heard of bacteria, parasites, or poisonous compounds. Yet your survival depends on detecting the effects of these invisible threats. The only tools available are your senses: sight, smell, taste, touch, and careful attention to what happens afterward. At first glance, these tools seem inadequate, yet they are more powerful than they appear. Human beings evolved in close contact with natural environments. Long before agriculture or cities, our ancestors spent every day interpreting subtle signals from landscapes. They learned to notice tiny differences that modern people often overlook entirely. A slight variation in leaf shape, an unusual smell from a damaged stem, changes in color during different seasons, patterns in where certain plants grow, the presence or absence of insects. Such details could carry important information. Many toxic plants advertise themselves in indirect ways. Some produce strong odors, others contain bitter compounds that trigger immediate rejection. Certain fruits display warning colors associated with unripe or chemically protected stages of development. While none of these signals are perfectly reliable, together they provide valuable clues. The challenge is that nature is rarely straightforward. Some deadly plants smell pleasant. Some poisonous fruits look delicious. Some dangerous mushrooms are nearly indistinguishable from edible species. The environment contains both genuine warnings and deceptive signals. This creates a constant tension between caution and opportunity. A cautious person avoids unnecessary risks but may miss valuable food sources. A bold person gains access to more resources but increases the chance of making fatal mistakes. human survival requires balancing both impulses. Anthropologists studying traditional foraging communities have often observed an interesting pattern. Expert gatherers rarely rely on a single identifying feature. Instead, they examine combinations of characteristics: shape, texture, location, season, growth patterns, associated species. Experience teaches them that one clue is rarely enough. What survives in the ethnographic record suggests that similar approaches may have deep prehistoric origins. The evidence remains incomplete, but complex environmental knowledge appears repeatedly wherever humans depend heavily on wild foods. In effect, people learn to read ecosystems rather than individual objects. A plant is not evaluated in isolation. It is understood as part of a larger context. This broader awareness may explain why many traditional food systems prove remarkably resilient over long periods. Knowledge becomes embedded not only in specific facts but also in ways of observing the world. One particularly fascinating strategy likely involved watching animals. At first glance, animal behavior seems like a useful guide. If birds eat a fruit safely, perhaps humans can too. If deer browse a particular plant, maybe it is harmless. If monkeys consume certain nuts or berries, their choices might reveal valuable information. Early humans almost certainly paid attention to such patterns. The problem is that animal biology differs dramatically from human biology. Many species tolerate toxins that would harm people. Birds can consume fruits containing compounds dangerous to mammals. Goats are famous for eating plants that would make humans severely ill. Some rodents can process toxins that would be fatal to larger animals. As a result, animal behavior offers clues but not certainty. Even today, the belief that all foods eaten by animals are automatically safe for humans remains dangerously incorrect. Prehistoric people likely discovered this fact through experience. Yet animal observation still retained value. Not because animals always provided answers, but because they sometimes revealed possibilities. A plant consistently ignored by every herbivore in an area might warrant caution. A fruit heavily consumed by multiple species might deserve investigation. The information was imperfect, but imperfect information was often better than none. The same principle extended beyond food. Water sources offered another opportunity for observation. Animals frequently visited reliable drinking locations. Following their trails could help humans locate water in difficult environments. But here again, appearances could deceive. Water suitable for one species was not necessarily safe for another. Parasites, contamination, and naturally occurring toxins remained hidden dangers. Nature constantly provided hints. Nature rarely provided guarantees. Taste became another critical tool. Human taste receptors evolved partly as defense mechanisms. Sweetness often signals calories. Saltiness indicates essential minerals. Sourness may suggest spoilage or unripe foods. Bitterness frequently warns of potentially harmful compounds. These preferences are not random. They reflect millions of years of evolutionary pressures. Yet even here the system is imperfect. Many poisonous substances taste bitter, but not all bitter substances are poisonous. Coffee is bitter. Dark chocolate is bitter. Numerous medicinal plants possess strong bitter flavors while remaining useful and safe when consumed appropriately. Human taste serves as an alarm system, not an absolute judge. The same applies to smell. Rotting meat often produces odors that trigger disgust. This reaction helps reduce exposure to pathogens and spoilage. However, not all dangerous foods smell bad, and not all unpleasant smells indicate danger. The environment remains filled with ambiguity. Perhaps that is the most important lesson. Modern people often imagine survival knowledge as a collection of simple rules. Eat this, avoid that. Safe here, dangerous there. Reality is far more complex. The earliest humans operated in a world where certainty was rare. Most decisions involved probabilities rather than guarantees. Knowledge reduced risk, but it could never eliminate it completely. This uncertainty shaped human psychology in profound ways. Many food taboos may have emerged from repeated encounters with danger. Certain plants became associated with illness. Particular preparation rituals developed because they seemed to improve safety. Traditions formed around caution, even when the underlying reasons were not fully understood. Some of these traditions survived for thousands of years. Others disappeared without leaving traces. Scholars still debate exactly how much prehistoric food knowledge relied on direct observation versus inherited cultural rules. No single explanation fully accounts for every society and environment. Yet evidence from around the world suggests that both processes work together. Observation generated information. Culture preserved it. Together they created a powerful survival system. Over time, humans became increasingly skilled at identifying dangerous foods before consuming them. Forests grew less mysterious. Rivers became more familiar. Seasonal cycles revealed patterns. The landscape transformed from a collection of unknown risks into a network of opportunities and warnings. But even the most observant people faced moments when knowledge collided with necessity. Because there was one force stronger than caution. One force capable of pushing individuals toward foods they would normally avoid. That force was hunger. And when hunger arrived, many of nature's warning signs became far easier to ignore. Knowledge is valuable. Experience is valuable. Caution is valuable. But none of them can fill an empty stomach. For most of human history, hunger is not an occasional inconvenience. It is a constant presence lurking at the edge of survival. Even in productive environments, food availability rises and falls with the seasons. Animals migrate. Fruit ripens and disappears. Rivers flood or dry out. Storms destroy resources. Droughts transform familiar landscapes into hostile territory. The difference between abundance and scarcity can arrive with startling speed. When food is plentiful, people can afford to be selective. Dangerous plants are ignored. Unfamiliar foods are approached cautiously. Risk remains manageable. When food becomes scarce, the calculation changes. A questionable route suddenly looks more appealing. A bitter fruit becomes worth considering. An unfamiliar seed may represent the difference between survival and starvation. This tension between caution and necessity shapes much of human prehistory. In modern societies, many people rarely experience true hunger. Missing a meal is uncomfortable, but alternatives usually exist. For prehistoric communities, especially those dependent on wild resources, periods of scarcity could become serious threats. A failed hunt might not matter once. A failed hunt repeated over days or weeks becomes dangerous. The archaeological record preserves numerous signs of these challenges. Ancient animal bones sometimes reveal periods when people targeted smaller and less desirable prey. Sites that once contained remains of large game gradually show increasing reliance on rabbits, rodents, fish, shellfish, or other secondary resources. Plant remains reveal similar patterns. Communities expand their diets when preferred foods become harder to obtain. These shifts suggest flexibility. They also suggest pressure. People are not suddenly eating unfamiliar foods because they are curious. Often they are doing so because circumstances leave few alternatives. The Ice Age provides some of the clearest examples. During the last glacial period, vast regions of the planet experienced dramatic environmental instability. Temperatures fluctuate, rainfall patterns change, vegetation zones shift. entire ecosystems reorganize over surprisingly short timescales. For human populations, these changes create uncertainty. A landscape rich in resources, one generation may become much less productive in the next. Groups are forced to adapt or move. In such circumstances, food knowledge becomes more than useful. It becomes essential. Communities capable of exploiting a wide range of resources possess an important advantage. They can fall back on secondary foods when primary resources fail. They can survive disruptions that might devastate more specialized populations. Yet many fallback foods come with challenges. Some are difficult to gather. Some require extensive processing. Others contain natural toxins. One of the most remarkable aspects of human survival is the willingness to invest extraordinary effort into making otherwise dangerous foods edible. Modern researchers have documented traditional societies processing toxic plants through elaborate methods that sometimes require hours or even days of work. At first glance, such practices seem inefficient. Why spend so much effort preparing food? The answer is simple. Because starvation is more dangerous. When hunger becomes severe enough, foods once considered marginal suddenly become valuable. Roots buried deep underground, bitter seeds, tough nuts, fibrous tubers, plants loaded with defensive chemicals. Resources ignored during good times become lifelines during difficult ones. This pattern appears repeatedly throughout human history. In Australia, Africa, the Americas, and many other regions, indigenous communities develop sophisticated methods for exploiting foods that outsiders initially consider inedible. Some plants require repeated washing. Others must be cooked extensively. Certain seeds are ground into flour only after toxins are removed. The final product may appear simple. The knowledge behind it is anything but simple. What survives in the ethnographic and archaeological records suggests that generations of experimentation often stand behind these techniques. Communities learn not only what can be eaten, but how it must be prepared. This distinction is crucial. Many foods are not simply safe or dangerous. They exist somewhere in between. A plant may be poisonous when raw but nutritious after cooking. A seed may contain harmful compounds that disappear after soaking. A root may become edible only after repeated processing. The difference between poison and nourishment often lies in technique. This realization represents one of the great turning points in humanity's relationship with food. Instead of merely identifying safe resources, people begin transforming dangerous ones. Nature provides the raw material. Human knowledge provides the solution. The implications are enormous. Every newly usable food source expands the carrying capacity of a landscape. Regions once considered marginal become more attractive. Seasonal shortages become easier to survive. Communities gain resilience. Yet hunger continues to exert pressure. Even the most knowledgeable groups face situations where choices become grim. Droughts offer a particularly powerful example. Archaeological evidence from various regions suggests that prolonged dry periods often coincide with dietary shifts. As preferred foods disappear, communities broaden their resource base. Sometimes this adaptation succeeds, sometimes it does not. The evidence remains incomplete, but certain sites contain signs of nutritional stress, reduced health, and increased mortality during periods of environmental hardship. These clues remind us that survival is never guaranteed. Knowledge improves the odds. It does not eliminate danger. One lesser-known detail emerges from studies of famine foods. Across many cultures, people preserve knowledge of emergency resources that are rarely consumed during normal years. These foods often require extensive preparation and may possess unpleasant taste or textures. In prosperous times, they are largely ignored. During crises, they become essential. Some of these traditions may preserve echoes of survival strategies stretching back thousands of years. The exact origins are often impossible to trace, but the pattern appears remarkably widespread. Human communities remember. They remember what can save them when better options disappear. Such memory becomes especially important because hunger affects decision-making itself. Modern research demonstrates that severe hunger changes behavior. It narrows attention. It increases risk-taking. It shifts priorities toward immediate needs. While prehistoric humans possessed the same cognitive abilities as modern people, they were not immune to these pressures. A starving person may accept dangers that a well-fed person would reject. This creates a dangerous cycle. The foods most likely to be considered during shortages are often the foods carrying greater risks. As desperation increases, caution weakens. The consequences can be severe. Some poisonous plants become attractive because they resemble familiar edible species. Others appear nutritious despite hidden toxins. Mistakes that seem unlikely during times of abundance become much more common when hunger dominates decision-making. Communities that survive repeated shortages therefore need more than food knowledge. They need systems for preserving discipline under pressure, rules, traditions, warnings, shared memory. These cultural safeguards help counteract the dangerous impulses produced by scarcity. Over generations, survival becomes a combination of environmental understanding and social organization. People learn not only what to eat, they learn when to eat it, how to prepare it, who should gather it, which parts to avoid, and under what circumstances exceptions can be made. The result is an increasingly sophisticated relationship with the natural world. Yet one mystery remains particularly fascinating. Even after identifying risky foods and learning when they can be consumed, humans still face a deeper challenge. Many of the world's most important plant foods remain chemically defended. They are full of compounds specifically evolved to discourage consumption. To unlock these resources, observation and caution are no longer enough. A new form of ingenuity is required. Humans must learn how to change the food itself. The root looks useless. It is hard, fibrous, bitter, and buried beneath dry soil. Digging it out requires effort. Chewing it raw produces an unpleasant taste. In some cases, it may even cause sickness. To many animals, this would be the end of the story. Humans, however, develop a different response. Instead of asking whether a food is immediately edible, they begin asking something far more powerful. Can it be made edible? This shift changes the course of human survival. At some point deep in prehistory, communities start discovering that dangerous foods are not always permanently dangerous. Certain plants can be altered, their harmful properties can be reduced, their nutrients can be unlocked. The transformation often requires patience, experimentation, and generations of accumulated knowledge, but the rewards are immense. A poisonous landscape begins to reveal hidden opportunities. The process probably unfolds gradually. A root left near a fire tastes different after heating. Seeds soaked in water become easier to digest. Certain nuts cause less illness after roasting. Tubers that were once bitter become more palatable after cooking. No single discovery creates a revolution. Instead, countless small observations accumulate across thousands of years. Together they form one of humanity's earliest practical sciences. Long before chemistry exists, people are conducting chemical transformations. They simply do not describe them in those terms. Fire plays a central role. The controlled use of fire is among the most important developments in human history, and one reason is its profound effect on food safety. Cooking alters proteins, destroys some pathogens, softens tough plant tissues, and changes the structure of many natural compounds. In some cases, cooking turns mildly toxic foods into valuable nutritional resources. This advantage is difficult to overstate. A plant that cannot be eaten raw may become edible after heating. A root that once caused digestive distress may become manageable. Seeds that are difficult to process suddenly release calories more efficiently. Fire expands the menu available to humans. It effectively increases the amount of usable energy present in an environment. What survives in the archaeological record suggests that cooking practices become increasingly sophisticated over time. Hearths appear across ancient sites. Burned plant remains reveal deliberate processing. Stone-lined cooking pits emerge in many regions. Communities are not merely consuming food, they are transforming it. Yet fire alone is not enough. Some of the world's most chemically defended foods require far more elaborate treatment. Consider the challenge presented by many wild seeds and grains. To modern eyes, seeds seem straightforward. They are small packages of stored energy. But from a plant's perspective, seeds represent the next generation. Protecting them is a matter of survival. As a result, many species fill their seeds with compounds that discourage consumption. These defenses can create bitterness, reduce digestibility, or interfere with nutrient absorption. Some are relatively mild, others are more serious. Early humans gradually learn methods to overcome them. Grinding becomes one solution. By breaking foods into smaller particles, grinding increases digestibility and allows additional processing techniques. Archaeologists have discovered grinding stones at sites tens of thousands of years old, suggesting that complex plant preparation begins surprisingly early. The significance of these tools extends beyond convenience. They reveal a willingness to invest labor in foods that are not immediately useful. A seed that appears worthless can become valuable after grinding, soaking, cooking, or combining with other techniques. Knowledge creates food where none seemed to exist before. Another remarkable strategy involves water. Soaking may sound simple, but it can dramatically alter certain foods. Harmful compounds dissolve or break down. Bitterness decreases. Texture improves. Nutrients become more accessible. Traditional societies around the world have independently developed soaking techniques for many different plant foods. Scholars still debate exactly when some of these practices originated, but the widespread nature of the pattern suggests deep historical roots. The evidence points toward repeated experimentation. People observe. They modify. They compare results. They remember what works. Generation after generation, methods improve. Perhaps the most extraordinary example involves leaching, a process used to remove toxins from certain plants. Acorns provide a famous case. In many regions, acorns are abundant but contain high levels of tannins, compounds that produce bitterness and can interfere with digestion. Raw acorns are far from ideal food. Properly processed acorns can become flour. This transformation requires considerable effort. The nuts are collected, shelled, ground, washed, and prepared through multiple stages. To outsiders unfamiliar with the process, the labor may appear excessive. To people living within these environments, the benefits are obvious. An abundant food source becomes available. A landscape once offering limited resources suddenly becomes richer. This same principle appears repeatedly throughout human history. Nature presents obstacles. Humans develop procedures. The obstacle becomes a resource. One lesser-known detail involves the role of accidental discoveries. Not every innovation results from deliberate experimentation. Some emerge through chance encounters. A basket of gathered roots left in water behaves differently. Seeds exposed to rain become easier to process. Food forgotten near a fire develops new characteristics. Unexpected outcomes occasionally reveal useful possibilities. Human curiosity then does the rest. When something works, people remember. When it works repeatedly, they teach others. Over time, accidents become traditions. Traditions become expertise. Expertise becomes culture. This process helps explain a curious feature of many traditional food systems. Practices that seem mysterious or unnecessarily complicated often have practical foundations hidden beneath generations of repetition. A preparation ritual may appear ceremonial. Its original purpose may have been toxin removal. A seemingly arbitrary sequence of steps may preserve critical safety information. The exact origins are often impossible to reconstruct, but many food traditions likely carry ancient solutions to ancient dangers. The challenge is that these solutions must remain accurate. A mistake during preparation can be disastrous. Removing toxins incompletely may leave food dangerous. Skipping essential steps may transform a safe meal into a harmful one. Knowledge, therefore, becomes inseparable from precision. Communities develop specialists, experienced gatherers, skilled processors, knowledgeable elders. Not everyone needs to understand every detail, but someone must preserve the expertise. In this way, food preparation becomes part of social organization itself. Survival increasingly depends on collective intelligence. The archaeological evidence hints at this growing complexity. As human populations spread into diverse environments, food processing technologies become more varied and sophisticated. Grinding stones, cooking pits, storage facilities, specialized tools, and other innovations appear across the prehistoric world. Each reflects accumulated solutions to environmental challenges. Each represents knowledge encoded into behavior. And behind each innovation lies a simple reality. Many of humanity's most important foods were not naturally welcoming. They had to be conquered, not through force, through understanding. Yet even as humans learn to transform roots, seeds, nuts, and tubers, they remain locked in an evolutionary contest with the organisms producing them. Plants are not passive resources waiting to be harvested. They are active participants in a struggle that has been unfolding for hundreds of millions of years. Every toxin tells part of that story. Every bitter taste is a clue. And the deeper humans explore the plant world, the more they discover that nature has been fighting back all along. The forest appears peaceful. Sunlight filters through leaves. Insects hum in the warm air. Fruits ripen quietly on branches. Seeds mature beneath protective shells. Roots thicken underground. To human eyes, especially modern ones, plants often seem passive. They do not chase prey. They do not roar, bite, or flee. Yet beneath this calm surface lies one of the oldest arms races on Earth. Plants have been defending themselves for hundreds of millions of years. Long before humans appeared, long before mammals became dominant, plants were already engaged in a constant struggle against creatures that wanted to eat them. Unable to run away, they evolved other solutions. Some grew thorns, some developed hard shells, others produced chemicals so unpleasant, toxic, or disruptive that herbivores learned to avoid them. These chemical defenses would eventually become one of the greatest challenges faced by human foragers. The remarkable thing is not that plants evolved toxins. The remarkable thing is how many different toxins they evolved. Modern science has identified thousands of plant compounds capable of affecting animal bodies. Alkaloids, cyanogenic glycosides, lectins, oxalates, tannins, and countless other substances appear throughout the botanical world. Some cause digestive distress, others interfere with the nervous system, some disrupt oxygen transport, others damage organs over time. Many evolved for a simple reason. Being eaten is bad for the plant. Natural selection therefore rewards defenses that reduce consumption. From the plant's perspective, a poisoned herbivore is a successful outcome. From the human perspective, it is a serious problem. What survives in the archaeological and ethnographic records suggests that early humans gradually became extraordinary students of these defenses. They learned not only which plants were dangerous, but how danger varied between species, seasons, plant parts, and preparation methods. This level of knowledge is easy to underestimate. In some environments, two plants may appear nearly identical while possessing dramatically different chemical properties. One may provide valuable nutrition, the other may cause severe illness. The ability to distinguish between them can determine survival. Even more challenging, a single plant may contain both useful and dangerous components. Certain fruits are edible while their seeds remain toxic. Some roots become safe after processing while leaves remain harmful. Young growth may differ chemically from mature growth. Nature rarely provides simple categories. Instead, it offers gradients, exceptions, and complications. Human communities learn to navigate these complexities through generations of accumulated observation. One fascinating example involves bitterness. As discussed earlier, bitterness often functions as a warning signal. Many toxic compounds activate bitter taste receptors. This relationship is so widespread that human sensitivity to bitterness likely evolved partly as protection against poisoning. Yet humans repeatedly develop ways to tolerate, reduce, or even appreciate bitter flavors. At first, this seems contradictory. Why embrace a signal associated with danger? The answer lies in nuance. Bitterness is often correlated with toxins, but it is not identical to toxicity. Some bitter foods are relatively harmless, others contain beneficial nutrients. Certain medicinal plants derive their usefulness from compounds that also produce bitterness. Over time, people learn that the warning signal requires interpretation. Not all bitterness means death. Not all pleasant flavors mean safety. Knowledge once again becomes more important than instinct alone. The relationship between humans and acorns illustrates this pattern beautifully. Across large parts of the world, oak trees produce enormous quantities of nuts. On paper, they appear to be ideal food sources. They are rich in calories, widely available, and often abundant. Yet they contain tannins. Raw acorns are frequently bitter and difficult to digest. Consuming large amounts without preparation can cause problems. For many animals, this defense works reasonably well. Humans respond differently. Instead of abandoning the resource, they invent methods to remove or reduce tannins. Washing, soaking, grinding, and other techniques transform a protected seed into a valuable staple. The plant evolved a defense. Humans evolved a cultural countermeasure. This pattern repeats across continents. Plants innovate. Humans adapt. Plants defend. Humans learn. The contest continues. Some of the most dramatic examples involve naturally occurring cyanogenic compounds. Certain plants contain chemicals capable of releasing cyanide under specific conditions. In sufficient quantities, cyanide interferes with the body's ability to use oxygen. The consequences can be severe. Yet several plant species containing these compounds become important food sources after careful preparation. The key word is careful. Improper processing may leave dangerous residues. Correct processing dramatically reduces risk. The difference between nourishment and poisoning can depend on knowledge passed from one generation to the next. Scholars still debate exactly how some of these techniques were first discovered. The evidence remains incomplete because prehistoric experimentation rarely leaves direct traces. What seems clear, however, is that such discoveries were not isolated accidents. Similar solutions emerge repeatedly in different parts of the world. Human populations confronted similar problems and often developed comparable answers. This convergence reveals something important about human adaptability. People do not simply endure environmental challenges, they actively solve them. One lesser-known aspect of plant defenses involves timing. Toxicity is not always constant. Some species become more dangerous during particular seasons. Others concentrate defensive compounds in specific tissues or developmental stages. A fruit may be hazardous when unripe and safe when mature. A root may be more toxic during drought conditions. Young leaves may differ significantly from older ones. For foragers, this means that identification alone is insufficient. Timing matters. The same plant can present different risks at different moments. Traditional ecological knowledge often reflects this reality with remarkable precision. Communities learn not only what to gather but when to gather it. Harvest seasons become linked to safety as well as availability. This temporal dimension adds another layer to humanity's growing food intelligence. The landscape becomes a calendar. People read seasonal changes the way modern societies read schedules. The consequences of getting the timing wrong can be serious. Yet despite all these challenges, humans continue expanding the range of plants they can safely exploit. Why, part of the answer lies in energy. Plants are everywhere. Large game animals may migrate, decline, or become difficult to hunt. Plant foods often provide more predictable access to calories. Learning to utilize them increases resilience. Another part of the answer lies in flexibility. A community capable of exploiting hundreds of plant species possesses options unavailable to specialists. When one resource fails, alternatives remain. This flexibility becomes a defining feature of human survival. Unlike many animals that depend heavily on narrow diets, humans increasingly become ecological generalists. They learn to draw nourishment from an astonishing variety of environments: tropical forests, savannas, temperate woodlands, deserts, mountain valleys, coastal wetlands. Each landscape presents unique challenges. Each demands unique knowledge. The accumulation of that knowledge represents one of humanity's greatest achievements. Yet plants are only part of the story. Even after mastering countless botanical defenses, people still face dangers from another source entirely. A successful hunt does not guarantee safety. A freshly killed animal can carry hidden threats of its own. Parasites, disease, spoilage, toxins concentrated within flesh and organs. The meal that appears safest may sometimes conceal dangers far less visible than a bitter root or poisonous berry. And as humans become increasingly skilled hunters, they discover that danger follows them onto the menu in ways they never expected. A successful hunt appears to solve everything. After days of uncertainty, a large animal finally falls. The hunters return carrying meat, fat, marrow, organs, skin, and bone. For a small prehistoric community, such a moment represents abundance. Calories arrive in concentrated form. Children eat, elders eat, energy returns. Survival feels secure, at least for a while. Yet hidden within that success is another set of dangers. The animal is dead. The race against time has begun. Modern refrigeration has altered humanity's relationship with meat so completely that it is easy to forget how fragile animal food truly is. Once an animal dies, countless microscopic processes immediately begin. Bacteria multiply. Tissues break down. Parasites remain active. Environmental conditions start determining how long the meat will remain safe. Prehistoric humans do not understand microorganisms. They do not know about bacteria, viruses, or parasitic life cycles, but they understand consequences. A meal consumed under the wrong conditions can produce sickness, weakness, or death. Through generations of observation, communities gradually learn that not all meat is equally safe. Freshness matters. Temperature matters. Preparation matters. The challenge is especially difficult because many dangers remain invisible. A poisonous berry often provides warning signs: bitter taste, unpleasant smell, distinctive appearance. Spoiled meat does not always reveal itself so clearly during its earliest stages. The human senses can detect many forms of decay, but not all of them. This uncertainty forces people to become careful observers once again. The smell of a carcass, the color of flesh, the presence of insects, changes in texture, environmental conditions, all become pieces of information used to estimate risk. What survives in ethnographic studies suggests that traditional hunting societies often possess extraordinarily detailed knowledge about animal condition. Hunters pay attention to signs that outsiders might never notice. Subtle differences can indicate whether meat remains suitable for consumption or should be avoided. This expertise develops because mistakes carry consequences, and some of those consequences are severe. One of the oldest dangers associated with meat is parasitism. Long before recorded history, parasites evolved complex strategies for moving between hosts. Many use prey animals as temporary habitats. When predators consume infected tissues, the parasites gain access to new bodies. Humans become part of this system. A healthy-looking animal may harbor worms, cysts, larvae, or microscopic organisms hidden within muscle and organs. Some parasites cause relatively mild symptoms. Others can produce serious illness. The evidence remains incomplete regarding the full range of prehistoric parasitic diseases, but archaeological studies have identified parasite remains in ancient human populations dating back thousands of years. The relationship between humans and parasites stretches deep into prehistory. Cooking becomes one of the most effective defenses. Heat destroys many parasites and pathogens. This benefit may have been just as important as improved flavor or digestibility. The widespread adoption of cooking likely reduced numerous foodborne dangers, though scholars still debate exactly how large its impact was in different regions and periods. What seems increasingly clear is that fire did more than make food easier to eat. It made food safer, yet even cooked meat could present problems. Some dangers originated before the hunt ever began. Predators occasionally accumulate toxins through their diets. Certain marine animals concentrate harmful substances from lower levels of the food chain. Fish and shellfish can become toxic under specific environmental conditions. In rare cases, consuming the wrong species at the wrong time may produce severe poisoning. Modern science continues to document such events. Ancient people encountered them without the benefit of laboratory analysis. Their protection came from experience. Communities remembered a particular fish species associated with illness, a season during which shellfish became risky, an organ that should be avoided, a preparation method that reduced danger. The exact origins of many such traditions are impossible to reconstruct, but similar patterns appear across cultures separated by vast distances. Repeated exposure generates practical knowledge. Practical knowledge becomes tradition. Tradition becomes survival. One lesser-known challenge involves the nutritional composition of animals themselves. Not all parts of an animal provide balanced nutrition. During times of scarcity, people sometimes consume foods that appear abundant but fail to meet physiological needs. A famous example involves extremely lean meat. Many large wild animals contain substantial protein but relatively limited fat during certain seasons. Consuming excessive amounts of lean protein without sufficient fat or carbohydrates can create serious metabolic stress. Early explorers in northern regions later described this phenomenon, sometimes calling it rabbit starvation. The name is somewhat misleading because the issue is not rabbits specifically. The problem is imbalance. Human bodies require more than protein alone. Prehistoric hunter-gatherers appear to have understood this reality through practice, even if they lacked scientific explanations. Fat-rich tissues were often highly valued. Marrow was extracted from bones. Organs received careful attention. Entire carcasses were utilized in ways that maximized nutritional returns. Nothing valuable was wasted. This efficiency reflects more than necessity. It reflects knowledge. People learned which parts provided the greatest benefits and which posed greater risks. Another challenge emerged from scavenging. Modern discussions of prehistoric diets often focus on hunting, but evidence suggests that ancient humans sometimes scavenged carcasses as well. A recently dead animal could provide valuable calories. It could also provide disease. Determining whether a carcass remained safe required judgment. How long had it been dead? What predators had already fed on it? What environmental conditions had affected it? The answers were not always obvious. Yet opportunities for food were too important to ignore entirely. Once again, survival depended on balancing risk and reward. The same pattern appears repeatedly throughout human history. Rarely are decisions made under perfect conditions. People operate with incomplete information. They estimate. They observe. They adapt. The ability to make reasonable decisions despite uncertainty becomes one of humanity's defining traits. Archaeological sites reveal hints of this flexibility. Ancient butchery marks show efficient processing techniques. Bone breakage patterns indicate systematic marrow extraction. Evidence of controlled fire suggests deliberate cooking practices. Together, these clues reveal communities constantly refining their relationship with animal foods. The process resembles an ongoing education. Every hunt teaches lessons. Every mistake teaches lessons. Every generation inherits a slightly larger body of knowledge. Over time, humans become remarkably effective at identifying, processing, and consuming animal resources. Yet meat and plants share an important similarity. Neither represents a guaranteed source of safety. Danger can still arrive from an unexpected direction. Not from food, not from predators, not from toxins hidden within roots or flesh, but from something seemingly much simpler, something so essential that no human can survive more than a few days without it. Water, clear water, cold water, flowing water. The very substance that sustains life can also become one of the most deceptive threats in the prehistoric world. And unlike a poisonous berry or spoiled carcass, its dangers often leave no visible trace at all. A stream winds through the landscape. The water is clear enough to reveal stones on the bottom. Sunlight flashes across its surface. Animals gather along its banks. Birds visit regularly. The scene appears reassuring, almost inviting. To thirsty travelers moving across unfamiliar terrain, such a place can seem like a gift, and often it is, but not always. One of the greatest challenges faced by prehistoric humans is that water does not need to look dangerous to be dangerous. Unlike a poisonous plant, which may advertise itself through bitterness or unpleasant effects, contaminated water frequently provides no warning at all. It can appear pure while carrying illness. It can look safe while concealing invisible threats. For much of human history, understanding this reality requires experience rather than science. The importance of water cannot be overstated. Humans can survive for weeks without food under certain conditions. Without water, survival becomes measured in days, In hot environments, the timeline shortens dramatically. Thirst exerts a pressure even more immediate than hunger. This urgency changes decision-making. A person faced with uncertain food can sometimes wait. A person deprived of water often cannot. The result is a constant balancing act between necessity and caution. Archaeological evidence suggests that access to reliable water sources strongly influenced human movement patterns throughout prehistory. Campsites frequently cluster near rivers, lakes, springs, wetlands, and coastlines. These locations provide obvious advantages. Water supports people. Water supports animals. Water supports plants. Where water exists, life tends to follow. Yet concentrations of life create their own problems. The same water source attracting humans may also attract countless other organisms. Animals drink there. They leave waste behind. Floods wash material into the water. Seasonal changes alter conditions. Stagnant pools become breeding grounds for parasites and microorganisms. None of these dangers are visible to the naked eye. The evidence remains incomplete regarding the exact disease burden experienced by early prehistoric populations, but scientists know that waterborne illness has shaped human history for thousands of years. Parasites, bacteria, and other pathogens likely posed recurring challenges long before anyone understood their existence. This presents an intriguing question. How did people identify safer water without knowing what contamination actually was? The answer appears to involve observation. Once again, humans become students of patterns. Certain water sources repeatedly produce illness. Others do not. Some remain reliable throughout the year. Others become problematic during specific seasons. Over generations, these observations accumulate into practical knowledge. Communities may not understand the underlying mechanisms, but they learn the outcomes. The distinction is important. Scientific explanation is valuable. Practical survival often depends first on recognizing patterns. A spring emerging directly from rock may gain a reputation for safety. A stagnant pond may acquire a reputation for danger. The exact reasons may remain mysterious, but the lesson survives. Many traditional societies possess extensive knowledge about local water conditions. Anthropologists have documented communities capable of identifying subtle differences between sources that outsiders perceive as identical. This expertise rarely appears overnight. It reflects generations of accumulated experience. One fascinating clue comes from animal behavior. Just as humans sometimes watch animals when evaluating food, they may also pay attention to animal interactions with water. Certain species consistently favor particular locations. Trails converge on reliable sources. Seasonal movements reveal hidden water supplies in arid environments. Yet here, as with food, animal behavior is not a perfect guide. Many animals tolerate pathogens and parasites differently than humans. A water source suitable for wildlife may still pose risks to people. Observation provides information. It does not provide certainty. Another challenge arises from geography itself. Not all dangerous water is contaminated by living organisms. Natural landscapes contain their own chemical hazards. Certain minerals occur at harmful concentrations. Volcanic regions may influence local water chemistry. Algal blooms can introduce toxins under the right conditions. Modern science can detect these dangers through laboratory analysis. Prehistoric humans rely on experience. Communities learn that some locations consistently produce illness, while others remain dependable. The precise causes may remain unknown, but patterns become embedded in cultural memory. This memory proves invaluable. A newcomer sees only a pond. A local resident sees generations of accumulated knowledge. One lesser-known aspect of prehistoric water use involves storage. Carrying water allows greater mobility, but stored water introduces additional challenges. Containers can become contaminated, stagnation can occur, environmental conditions influence quality. The archaeological evidence for early water storage is fragmentary, because many containers were made from organic materials that rarely survive. Nevertheless, researchers believe that various forms of water transport and storage likely emerged in many prehistoric societies. With these innovations come new opportunity and new risks. The pattern is familiar by now. Every solution creates fresh challenges. Every adaptation requires further knowledge. Perhaps the most important development is the growing connection between fire and water. Boiling water may seem obvious today, but recognizing its benefits would have profound consequences. Heat can destroy many pathogens, making questionable water safer to consume. The exact timeline remains debated among scholars. Direct archaeological evidence is difficult to obtain because boiling itself rarely leaves clear traces. However, once cooking technologies become widespread, opportunities for heating water increase dramatically. Whether through deliberate purification or incidental effects during food preparation, fire likely contributed to reducing some waterborne dangers. Again, knowledge expands human options. The environment remains hazardous. Human ingenuity makes it more manageable. Water also reveals an important truth about survival. The greatest threats are not always dramatic. Popular imagination often focuses on predators, venomous animals, or deadly plants. These dangers are real, but they are visible. They command attention. Invisible dangers often cause greater cumulative harm. A contaminated stream, a parasite hidden in water, a pathogen carried unknowingly from one source to another. Such threats operate quietly. Their effects accumulate over time. For prehistoric communities, learning to navigate these risks may have been just as important as mastering hunting or gathering. The challenge becomes even more complex because knowledge cannot reside in a single individual. No one person can remember every safe plant, every dangerous route, every seasonal warning, every hunting lesson, every reliable spring, and every preparation technique. Survival increasingly depends on collective memory. The wisdom of the group becomes more valuable than the knowledge of any single member. And within that growing network of memory, certain individuals begin playing a particularly important role. Not necessarily the strongest hunters, not necessarily the fastest gatherers, but the people who remember, the people who teach, the people who carry decades of accumulated experience through changing seasons and changing landscapes. Because in a world where every meal and every drink can carry hidden risks, knowledge itself becomes one of humanity's most precious resources. And nowhere is that more apparent than in the relationship between generations. In a prehistoric camp, knowledge does not sit on shelves. There are no books, no maps, no written recipes, no field guides explaining which berries are safe, which routes require soaking, or which water sources should be avoided after heavy rains. Everything exists inside human minds. This simple fact changes the importance of age. In many modern societies, physical strength and productivity often receive the most attention. In prehistoric communities, experience can be equally valuable. Sometimes it is even more valuable. A person who remembers where food appears during droughts, which plants become edible after frost, or how to process a dangerous route may contribute as much to survival as a successful hunter. Knowledge becomes a resource, and the people who carry it become essential. This is particularly true because environmental information accumulates slowly. A single season teaches only a few lessons. a decade teaches many more. A lifetime spent observing landscapes, weather patterns, animal behavior, and food resources creates a storehouse of information difficult to replace. An elder who remembers previous droughts may recognize warning signs others overlook. A skilled gatherer may know which emergency foods remain available when preferred resources fail. A grandmother may understand preparation techniques whose origins stretch back through generations. These forms of expertise rarely leave archaeological traces. Stone tools survive. Bones survive. Hearths survive. Memory does not. Yet many anthropologists believe that the transmission of knowledge represents one of the most important foundations of human survival. Without it, every generation would begin almost from scratch. Imagine the consequences. Children would need to rediscover edible plants independently. Dangerous mistakes would repeat endlessly. Preparation methods would disappear whenever experienced individuals died. Communities would lose critical information with alarming frequency. Human expansion into diverse environments would become far more difficult. The persistence of complex food traditions suggests that something very different occurs. Knowledge is preserved. Knowledge is taught. Knowledge accumulates. This process begins in childhood. Young humans occupy a unique position among mammals. Compared to many species, human children require extraordinarily long periods of learning before reaching full independence. This extended childhood is expensive from an evolutionary perspective. Children consume resources for years before contributing fully to group survival. Yet the investment offers advantages. A longer learning period allows the acquisition of enormous amounts of information. Food knowledge forms a significant part of that education. Children learn through observation. They watch adults gather plants. They accompany older relatives during foraging trips. They observe preparation techniques. They absorb warnings. Over time, what initially appears as a confusing landscape gradually becomes understandable. A meadow transforms into a catalogue of resources. A forest becomes a map of opportunities and hazards. The process is slow, but it is remarkably effective. Researchers studying traditional societies often observe children acquiring environmental knowledge gradually over many years. By adulthood, individuals may possess astonishing familiarity with local ecosystems. The exact details vary between cultures, but the broader pattern remains consistent. Learning is not optional. Learning is survival. One fascinating aspect of this system is redundancy. Critical information is often shared by multiple individuals rather than stored in a single expert. If knowledge exists only in one person, the death of that person creates a dangerous vulnerability. Distributed knowledge is safer. Multiple elders may know emergency foods. Several family members may understand preparation techniques. Warnings become embedded in stories, habits, and daily routines. As a result, information survives even when individuals do not. This resilience may help explain the extraordinary longevity of some traditional food practices. Certain techniques persist across centuries and, in some cases, millennia. Their original inventors are forgotten. The knowledge remains. One lesser-known detail involves the role of older adults after their peak reproductive years. Humans are unusual among primates in having significant numbers of individuals who survive well beyond child-rearing age. Scientists have proposed various explanations for this pattern. One influential idea suggests that older individuals contribute valuable knowledge and support to younger generations. The evidence remains debated, and no single explanation fully accounts for human longevity. But many researchers believe cultural transmission plays an important role. In practical terms, an elder may provide something that no young hunter can: perspective, memory, historical context, knowledge of rare events. A severe drought occurring once every 20 years may be remembered by older community members even when younger individuals have never experienced anything similar. That memory can influence critical decisions: where to move, what foods to prioritize, which risks to avoid. The value of such information increases dramatically during periods of environmental instability. Throughout prehistory, climate fluctuates repeatedly. Glacial advances and retreats reshape landscapes. Rainfall patterns shift. Ecosystems reorganize. Human communities must continually adapt. Cultural memory helps them do so, not perfectly, not always successfully, but often enough to make a difference. The archaeological record occasionally offers indirect hints of this process. Human populations repeatedly survive environmental disruptions that might otherwise appear catastrophic. The reasons are complex and vary from region to region, but accumulated knowledge almost certainly contributes. Communities remember what worked before. They apply those lessons again. Food knowledge also acquires social significance. The act of teaching strengthens relationships. Shared meals reinforce trust. Preparation techniques become communal activities. Information spreads not only through formal instruction but through participation. People learn by doing. This creates an important advantage. Knowledge becomes woven into daily life. A child helping process seeds absorbs information naturally. Someone gathering roots with experienced relatives learns without needing explicit lectures. The landscape itself becomes a classroom. Such systems prove remarkably effective for preserving practical expertise, yet they also introduce challenges. Information can change over time. Details can be forgotten. Mistakes can spread. Traditions may persist even after environmental conditions change. Human knowledge is powerful, but it is not perfect. Communities must continually balance inherited wisdom against new observations. This tension between tradition and adaptation appears throughout human history. A method that worked for generations may suddenly become less effective under changing circumstances. A familiar food source may disappear. A new resource may become available. Survival requires both memory and flexibility. Neither alone is sufficient. Perhaps that combination represents one of humanity's greatest strengths. People preserve lessons from the past while remaining capable of innovation. They remember, they experiment, they teach, they revise. This ongoing process allows food knowledge to expand far beyond simple lists of edible species. Over time, humans begin noticing something even more intriguing. Some substances capable of causing illness under one set of conditions can produce benefits under another. A poisonous plant may become a medicine. A toxic compound may help during hunting. A dangerous substance may serve purposes unrelated to nutrition entirely. The boundary between poison and usefulness turns out to be far less clear than it first appears. And as human understanding deepens, one of the strangest chapters in the history of survival begins to unfold. Not every poison is simply a poison. At first glance, this idea seems contradictory. For generations, early humans learned to fear toxic plants, dangerous roots, contaminated water, and harmful animal products. Survival depends on avoiding substances capable of causing sickness or death. The safest strategy would appear to be simple avoidance. Yet human curiosity rarely stops at avoidance. Over time, people begin noticing something strange. Certain substances that cause harm in large amounts produce very different effects in small amounts. A plant that becomes dangerous when consumed freely may influence pain, alertness, digestion, or perception when used carefully. A toxin that kills prey animals may become useful during hunting. A bitter root avoided as food may possess other properties worth understanding. The line separating poison from medicine is often thinner than it appears. Modern pharmacology continues to demonstrate this reality. Many powerful medicines originate from compounds that can also be dangerous under different circumstances. Dosage matters, preparation matters, context matters. Prehistoric people do not possess laboratories or chemical analysis. What they possess is observation, and observation can reveal surprising things. Imagine a community that repeatedly encounters a particular plant. Eating large amounts causes illness. That lesson becomes well established. Yet someone notices that a much smaller quantity produces different effects. Perhaps discomfort decreases. Perhaps energy changes. Perhaps certain symptoms become less severe. No scientific theory exists to explain the phenomenon. The observation itself is enough. Over generations, such discoveries accumulate. The evidence remains incomplete because organic materials rarely preserve well in archaeological contexts. But ethnographic studies from around the world reveal extensive traditional knowledge regarding medicinal plants. Many societies develop sophisticated understandings of local flora long before modern medicine emerges. Some of this knowledge likely has very ancient roots. Scholars continue debating exactly how far back specific practices extend, but the broader pattern is difficult to ignore. People learn that plants are not simply food or non-food. They possess multiple uses. A single species may provide nutrition, medicine, fiber, dyes, tools, or ritual significance depending on how it is prepared and applied. This realization dramatically expands humanity's relationship with the natural world. The environment becomes more than a source of calories. It becomes a source of solutions. One fascinating example involves compounds affecting the nervous system. Many plants evolved chemicals specifically designed to discourage herbivores. These compounds interact with animal biology in powerful ways. In high concentrations, they may be dangerous. In lower concentrations, they may produce effects that humans learn to exploit. The exact pathways through which such knowledge develops remain uncertain. No single explanation fully accounts for the diversity of traditional medicinal systems found throughout the world. What survives in the record suggests a mixture of experimentation, observation, cultural transmission, and accumulated experience. The process resembles food discovery in many respects. People notice patterns. Patterns become knowledge. Knowledge becomes tradition. The same dynamic appears in hunting. Long before metal weapons or modern technologies, hunters face a difficult problem. Large animals can be dangerous. Bringing them down efficiently reduces risk and conserves energy. Some communities discover that naturally occurring toxins can help. Certain plants contain compounds capable of weakening, disabling, or killing animals when applied appropriately. Poisoned arrows, darts, and other hunting tools emerge in various parts of the world. This development represents a remarkable shift in perspective. A substance once feared becomes an asset. The danger remains. Its purpose changes. Such innovations reveal an increasingly sophisticated understanding of the environment. Humans are no longer merely defending themselves against natural toxins. They are learning to use those toxins strategically. This requires precision. A hunting poison must be handled carefully. Knowledge of preparation becomes critical. Mistakes remain possible, yet the benefits can be substantial. The broader lesson is that survival knowledge grows more complex over time. Early stages focus primarily on identifying danger. Later stages involve managing it. Eventually, people begin harnessing it. One lesser-known detail concerns the psychological effects of certain plant compounds. Throughout history, various societies have used naturally occurring substances during rituals, ceremonies, healing practices, and social activities. The exact origins of these traditions are often difficult to determine. Archaeological evidence can be ambiguous. Organic residues degrade. Interpretations remain debated. Nevertheless, many researchers believe that humans have experimented with mind-altering plants for thousands of years. This experimentation likely carried risks. Some substances are relatively safe under controlled conditions. Others are not. The distinction once again depends on knowledge, preparation methods, dosage, context, cultural safeguards. Without these elements, danger increases dramatically. With them, communities sometimes integrate powerful substances into broader social systems. The same principle appears repeatedly. Knowledge transforms risk into opportunity. Not perfectly, not without cost, but often successfully enough to endure. This growing sophistication also changes how people think about illness itself. A community repeatedly observing the effects of certain plants may begin associating particular remedies with particular conditions. Scientific explanations remain absent, yet practical relationships emerge. A root appears helpful for digestive discomfort. A leaf preparation seems useful for wounds. A bark extract produces noticeable effects. Some treatments genuinely work. Others may rely more on belief, coincidence, or placebo effects. Distinguishing between them is difficult without modern research. Even today, scholars continue evaluating traditional remedies to determine which possess measurable biological activity and which do not. The results are often surprising. Numerous modern medicines trace their origins to traditional observations accumulated over generations. This does not mean ancient people possessed complete medical understanding. Far from it. The evidence remains incomplete, and many historical practices were ineffective or harmful. Yet dismissing prehistoric knowledge would be equally mistaken. Communities surviving in challenging environments often develop remarkably accurate insights into local resources. Their knowledge emerges from repeated interaction with reality. Failures are costly. Successes are remembered. Over long periods, useful information tends to persist. Perhaps the most remarkable aspect of all this is the sheer amount of information involved. By now, human survival depends on an enormous body of knowledge. Safe foods, dangerous foods, preparation methods, seasonal timing, medicinal uses, hunting applications, water sources, emergency resources. The list grows continuously. No individual discovers everything. Knowledge becomes cumulative. Each generation inherits lessons from the previous one and adds new observations of its own. This process allows cultural adaptation to move far faster than biological evolution. Yet biology has not been standing still. While humans are learning about their environments, their bodies are changing as well. Across thousands of generations, populations exposed to different foods, toxins, and ecological conditions begin developing subtle biological differences. Some people become better equipped to process certain foods. Others gain advantages in particular environments. The relationship between culture and biology grows increasingly intertwined, and in the long struggle to survive a world where every meal could be dangerous, adaptation begins leaving traces not only in memory and tradition, but within the human body itself. For much of this story, survival has seemed like a triumph of learning. Humans observe dangerous plants, they remember poisonous berries, they invent preparation techniques, they share knowledge across generations. Culture becomes a shield against uncertainty. Yet another process has been unfolding in the background the entire time. While humans are changing their behavior, evolution is changing humans. Not quickly, not dramatically enough for any individual to notice. But across thousands of generations, the relationship between people and food begins leaving marks on the body itself. This interaction between culture and biology is one of the most fascinating aspects of human history. Many animals survive because their bodies are highly specialized. Koalas process eucalyptus leaves. Pandas consume bamboo. Other species evolve around narrow dietary niches. Humans take a different path. Instead of specializing in a single resource, they become extraordinary generalists. Part of that flexibility comes from intelligence and culture. Part of it comes from biology. The two are inseparable. Even before the emergence of modern humans, evolutionary pressures are shaping sensory systems involved in food selection. Taste receptors provide one example. As discussed earlier, humans possess specialized receptors capable of detecting bitterness, sweetness, saltiness, sourness, and other chemical signals. These systems did not appear by accident. Natural selection favored individuals better able to recognize useful nutrients and avoid harmful substances. A sweet fruit often signals calories. A bitter leaf may signal danger. The relationship is imperfect, but over evolutionary timescales, even imperfect advantages matter. People who avoid lethal mistakes survive more often. Their descendants inherit similar tendencies. The result is a species equipped with biological tools for navigating dietary uncertainty. Yet these tools are only the beginning. One of the most intriguing discoveries in modern genetics is the extent to which human populations have adapted to local food environments. The best-known example involves milk. For most mammals, the ability to digest lactose declines after weaning. Humans originally followed the same pattern. However, in some populations that developed pastoral lifestyles, genetic changes allowed many adults to continue digesting milk efficiently. This adaptation appears relatively recent in evolutionary terms. It emerges after the domestication of livestock. Culture changes first. Biology follows. The story illustrates a broader principle. Human innovations create new evolutionary pressures. New pressures create opportunities for adaptation. The relationship works in both directions. Although lactose digestion is a comparatively late development, similar interactions likely occurred much earlier with other foods. Consider plant toxins. Humans have long consumed plants containing defensive chemicals. Many of these compounds require processing by enzymes within the body. Genetic variation influences how efficiently individuals handle such substances. Modern populations show differences in various metabolic pathways associated with diet. The exact evolutionary histories remain complex and are still being investigated, but the broader pattern suggests ongoing interactions between human biology and local food environments. No single explanation fully accounts for every population or every adaptation. Evolution rarely works so neatly. Nevertheless, the evidence increasingly points toward a dynamic relationship between people and what they eat. Food shapes bodies. Bodies influence food choices. The cycle continues. One lesser-known example involves starch digestion. Research has revealed variation in genes associated with the production of salivary amylase, an enzyme that begins breaking down starches in the mouth. Populations with long histories of starch-rich diets often show higher average copy numbers of these genes. The implications are significant. Foods are not merely cultural resources. They become evolutionary forces. The roots, tubers, seeds, and grains that prehistoric people learned to exploit may eventually influence human biology itself. Again, culture opens the door. Evolution responds. This process extends beyond digestion. Certain environmental toxins create selection pressures as well. Plants produce compounds capable of affecting liver function, metabolism, and other physiological systems. Individuals differ naturally in their ability to process such substances. Over long periods, repeated exposure may influence which genetic traits become more common within populations. The details are often difficult to reconstruct. Ancient DNA provides valuable clues, but many questions remain unresolved. Scholars still debate the strength and timing of various dietary adaptations. The evidence remains incomplete. What seems increasingly clear, however, is that human survival cannot be understood solely through culture or solely through biology. Both matter. Neither tells the entire story. The interaction between them helps explain humanity's extraordinary success. A purely biological solution would have been too slow. Environmental conditions changed rapidly. Humans migrated constantly. New foods appeared faster than evolution could redesign bodies. Culture provided flexibility. People learned. They shared knowledge. They invented techniques. At the same time, biology continued making smaller adjustments in the background. The combination proved remarkably effective. Another fascinating area involves taste itself. Not everyone experiences flavors in exactly the same way. Genetic differences influence sensitivity to certain bitter compounds. Some individuals perceive particular substances as intensely unpleasant. Others find them relatively mild. Researchers continue exploring how these variations may have influenced food preferences and survival strategies throughout human history. A heightened sensitivity to bitterness might reduce the risk of consuming toxins. It might also discourage the use of valuable food resources. Once again, trade-offs appear. Nature rarely offers perfect solutions. The same complexity emerges with alcohol metabolism, caffeine sensitivity, and numerous other food-related traits. Human populations carry traces of long interactions with diverse environments. Each adaptation tells part of a larger story. A story of experimentation stretching across millennia. Yet even the most successful adaptations have limits. Knowledge fails, bodies fail, environmental conditions change. Throughout prehistory, communities occasionally encounter situations where accumulated wisdom proves insufficient. A familiar food source disappears. A climate shift alters ecosystems. A drought pushes people toward risky alternatives. A preparation technique is forgotten. The consequences can be profound. Food-related mistakes do not always affect individuals alone. Sometimes entire communities suffer. Sometimes migrations begin because local resources become unreliable. Sometimes traditions change because old methods no longer work. Sometimes settlements are abandoned. The archaeological record contains scattered hints of such moments. They rarely announce themselves clearly. Instead, they appear as subtle patterns. Dietary changes, population movements, shifts in resource use, signs of nutritional stress. Each clue suggests that survival remained uncertain despite all human ingenuity. The struggle was never completely won. And in certain cases, mistakes involving food, water, or environmental knowledge may have reshaped the destinies of entire groups. Those moments are harder to see. But when the evidence does emerge, it reveals just how fragile human survival could be in a world where one wrong meal might trigger consequences far beyond a single life. Most mistakes disappear without a trace. A person becomes sick after eating the wrong plant. A family suffers through a contaminated meal. A hunter consumes spoiled meat and never fully recovers. Such events may have altered individual lives, but archaeology rarely preserves enough evidence to identify them thousands of years later. The ground remembers bones more easily than it remembers meals. Yet occasionally, the consequences of food-related decisions become large enough to leave visible marks in the historical and prehistoric record. When that happens, a different picture emerges. The story is no longer about individual survival. It becomes a story about entire communities confronting environmental uncertainty. One of the most important realities of prehistoric life is that food systems are rarely static. Landscapes change, climate changes, animal populations fluctuate, plants migrate, rivers alter their courses. What worked for generations may suddenly become less reliable. Human societies must adapt. Sometimes they do so successfully. Sometimes adaptation arrives too late. The archaeological record contains numerous examples of communities broadening their diets during periods of stress. Preferred foods decline. Alternative resources become more important. Hunting strategies shift. Gathering patterns change. At first glance, these adjustments appear minor. In reality, they may signal major challenges. Imagine a population that has relied heavily on a particular resource for centuries. Perhaps large grazing animals dominate local diets. Then environmental conditions begin changing. Vegetation patterns shift. Animal numbers decline. Migration routes move elsewhere. The old system becomes less dependable. People respond by expanding their food base. Smaller animals, fish, shellfish, wild plants, roots, seeds, nuts. The transition may help preserve survival, but it also requires new knowledge, new labor patterns, and new risks. Archaeologists sometimes refer to this broadening process as dietary diversification. Evidence appears in many parts of the world. Communities begin exploiting resources previously considered secondary or marginal. This adaptation often demonstrates remarkable resilience, yet it can also reveal pressure. A wider diet sometimes indicates opportunity. At other times it reflects necessity. Distinguishing between the two remains one of archaeology's ongoing challenges. The evidence rarely speaks clearly. What survives in the record suggests that environmental disruptions repeatedly forced humans to reconsider their relationships with food. One striking example comes from periods of prolonged drought. Water scarcity affects nearly every aspect of survival. Plant productivity declines. Animal populations shift. Reliable food sources become harder to predict. Under such conditions, communities may turn increasingly toward emergency foods. As discussed earlier, many of these resources require extensive preparation. Some contain toxins. Others provide limited nutrition. The ability to exploit them can prevent starvation, but relying on them permanently may prove difficult. Signs of nutritional stress occasionally appear in ancient skeletal remains. Researchers find evidence of interrupted growth, periods of malnutrition, and other indicators of hardship. Interpreting these clues requires caution because many factors can produce similar patterns. No single explanation fully accounts for every case. Still, the broader picture is clear. Food security remained fragile. Even knowledgeable communities could be pushed toward their limits. One lesser-known detail emerges from studies of ancient teeth. Dental remains preserve surprisingly rich information about past diets, where patterns, chemical signatures, and microscopic residues reveal shifts in food consumption over time. Sometimes these shifts occur gradually. Sometimes they appear abruptly. A sudden change in dietary evidence may suggest environmental disruption, migration, cultural transformation, or resource shortages. The exact cause often remains debated. What matters is that food choices leave traces, and those traces reveal communities constantly adjusting to changing circumstances. Another challenge involves the loss of knowledge itself. Modern people often assume that useful information naturally accumulates over time. In reality, knowledge can disappear. A preparation technique may be forgotten if a population declines. A migration may separate people from familiar resources. A community entering a new environment may encounter foods requiring entirely different expertise. The consequences can be serious. Imagine arriving in a landscape filled with unfamiliar plants. The knowledge accumulated over generations in one ecosystem suddenly becomes less useful in another. New lessons must be learned. Some are learned quickly. Others take decades or centuries. The process is rarely smooth. Human history contains many examples of populations moving into unfamiliar environments and gradually developing new survival strategies. The archaeological evidence suggests that adaptation often involved experimentation, innovation, and occasional failure. This pattern appears repeatedly during major migrations. Groups entering new territories face unfamiliar species, unfamiliar climates, and unfamiliar risks. Every successful settlement requires the construction of new ecological knowledge. In effect, parts of the learning process begin again. The challenge is particularly visible in island environments. When humans arrive on isolated islands, they often encounter ecosystems unlike anything they have previously known. New plants, new animals, new seasonal patterns. Sometimes these environments provide abundant opportunities. Sometimes they conceal unexpected dangers. The evidence remains incomplete, but archaeologists continue uncovering examples of communities adapting to highly unusual ecological conditions. Their success often depends on flexibility. The ability to learn quickly becomes critical. Food-related mistakes can also influence social organization. A dangerous plant requiring careful preparation encourages cooperation. Complex processing techniques demand shared labor. Knowledge becomes concentrated in experienced individuals. Communities develop systems for teaching and preserving information. The larger and more complex the food system becomes, the more valuable social coordination becomes. Survival increasingly depends not only on knowing what to eat, but on maintaining the structures that preserve that knowledge. This reality may help explain why food traditions often remain remarkably conservative. Changing established practices can introduce risk. If a preparation method has kept generations alive, abandoning it casually would be dangerous. Traditions therefore serve practical purposes as well as cultural ones. They act as storage systems for accumulated experience. Yet traditions cannot remain entirely static. The environment continues changing. New opportunities appear. New challenges emerge. Successful societies balance caution with innovation. They preserve proven knowledge while remaining willing to adapt. That balance may represent one of humanity's greatest strengths. It allows communities to survive disruptions that might overwhelm more rigid systems. And over long periods, it enables something extraordinary. Knowledge begins traveling far beyond the boundaries of individual groups. Food wisdom no longer remains trapped within isolated communities. As people migrate, trade, meet strangers, and exchange ideas, survival knowledge starts spreading across regions, carrying lessons learned through countless generations of experimentation. The library that once existed within a single camp gradually becomes something much larger. For most of human history, knowledge travels at the speed of people. There are no books to carry information across continents, no written manuals explaining how to prepare a poisonous root, no maps identifying safe water sources. Every lesson moves through conversation, observation, imitation, and memory. At first, this limits the spread of survival knowledge. A community may possess generations of expertise unavailable to anyone living beyond the next mountain range. Yet humans rarely remain isolated forever. People migrate. They trade. They marry into neighboring groups. They encounter strangers. And whenever such encounters occur, information has the opportunity to move as well. This process becomes one of the most important forces shaping human survival. Imagine two communities meeting along a river valley thousands of years ago. Their languages may differ, their customs may differ, their histories may be entirely separate. Yet both must solve the same fundamental problem: finding food without dying from it. One group may possess expertise regarding local plants. The other may understand fishing techniques unknown to their neighbors. Over time, pieces of knowledge can pass between them, not all at once, not necessarily intentionally, but gradually. A useful preparation method is observed. A gathering technique is copied. A warning is shared. A new food enters the local diet. The cumulative effect can be profound. What begins as a local discovery sometimes spreads far beyond its place of origin. Archaeological evidence increasingly suggests that prehistoric people maintained broader social connections than earlier researchers once assumed. Trade networks carried stone, shells, pigments, and other materials across surprisingly large distances. Where goods move, information often follows. The exact details remain debated because ideas leave fewer traces than physical objects. Still, the pattern appears repeatedly throughout human history. Knowledge travels, and survival knowledge may be among the most valuable forms of information exchanged. One fascinating example involves plant processing techniques. Across different parts of the world, communities independently develop methods of detoxifying difficult foods. Some solutions appear to arise locally. Others may spread through contact. Determining which is often challenging. No single explanation fully accounts for every case. Yet the broader trend is clear. Human populations rarely solve problems entirely alone. Ideas move between groups. Successful innovations have a tendency to spread. This diffusion creates an important advantage. A community no longer needs to learn every lesson through direct experience. It can benefit from discoveries made elsewhere. In practical terms, this means fewer dangerous experiments, fewer repeated mistakes, more rapid adaptation. The sharing of food knowledge may therefore have increased survival far beyond the immediate benefits of any particular discovery. One lesser-known aspect of this process involves migration itself. When people move into new environments, they do not arrive empty-handed. They bring knowledge accumulated in previous landscapes. Sometimes that knowledge transfers successfully. Sometimes it does not. A preparation technique useful in one ecosystem may have little relevance in another. Familiar plants disappear. New species appear. Old assumptions require revision. Migration therefore creates both opportunities and challenges. People carry information across great distances, but they must also learn new information upon arrival. The result is a constant process of cultural adaptation. This adaptability becomes one of humanity's defining characteristics. Consider the extraordinary range of environments occupied by prehistoric populations. Tropical rainforests, arid deserts, mountain regions, grasslands, coastal wetlands, Arctic tundra. Each demands specialized knowledge, yet humans eventually thrive in all of them. Part of the explanation lies in cultural flexibility. People borrow useful ideas. They modify them. They combine them with local observations. Knowledge grows through accumulation rather than replacement. The process resembles a river gathering tributaries. Every encounter adds something. Every generation contributes something. Over time, the body of survival knowledge becomes vast. Archaeological discoveries occasionally reveal hints of these exchanges. Similar tool types appear across large regions. Processing technologies spread. Evidence of long-distance contact emerges in unexpected places. Material goods provide visible clues. The movement of ideas is harder to see, yet it may be even more important. A traded stone blade is valuable. Knowledge about avoiding poisonous plants may save lives for generations. The comparison is difficult to ignore. Food knowledge also travels through stories. Human beings are natural storytellers. Long before writing, narratives help preserve information. A memorable story is easier to remember than a list of instructions. Many traditional cultures embed practical lessons within myths, warnings, and oral histories. A tale about a dangerous location may preserve information about contaminated water. A story involving a particular plant may encode harvesting rules. A narrative explaining seasonal behavior may reflect ecological observations accumulated over centuries. Modern researchers must approach such interpretations carefully. Not every story conceals practical knowledge, yet many clearly contain environmental information. The boundary between cultural tradition and survival strategy is often difficult to separate. For prehistoric communities, the distinction may not have mattered. The lesson survives either way. Another remarkable feature of these knowledge networks is redundancy. Important information often exists in multiple forms. People learn through direct observation. They learn through participation. They learn through stories. They learn through rituals. They learn through daily practice. This redundancy increases resilience. If one pathway fails, others remain. The system is surprisingly robust, yet it is never perfect. Misunderstandings occur, details change, information degrades, false beliefs can spread alongside useful ones. Human cultural transmission is powerful, but it is not infallible. The evidence remains incomplete regarding how prehistoric communities distinguished reliable knowledge from unreliable knowledge. However, one mechanism appears repeatedly throughout history. Reality acts as a filter. Methods that consistently produce safe food tend to survive. Methods that repeatedly cause harm tend to disappear. Not always, not immediately, but often enough to shape long-term outcomes. Survival itself becomes a form of testing. This process helps explain why some food traditions persist for extraordinary length of time. They continue because they work. Perhaps not perfectly, perhaps not for reasons fully understood by their practitioners, but well enough to endure. As centuries become millennia, these accumulated lessons spread across landscapes and populations. The human relationship with food grows increasingly sophisticated. Dangerous plants become staples after proper processing. Risky environments become manageable through experience. New ecosystems become intelligible through learning. The world remains full of poisons. Humans become better at navigating them. And yet one final mystery remains. After thousands of years of experimentation, observation, adaptation, and cultural exchange, traces of these ancient struggles continue to survive. Not only in archaeology, not only in traditional societies, but in kitchens, customs, and habits that still exist today. The distant past has not vanished entirely. Fragments of it remain hidden within everyday life, quietly preserving memories of a time when every meal carried the possibility of disaster. A modern kitchen seems very far removed from prehistory. Bright lights replace campfires. Refrigerators hum quietly in the background. Packaged foods arrive with labels, expiration dates, nutritional information, and safety regulations. Most people never need to identify edible roots in a forest or determine whether a stream carries hidden dangers. Yet beneath this layer of modern convenience, ancient survival lessons remain surprisingly visible. Many of the food traditions practiced around the world today carry echoes of a much older struggle. A struggle against hunger, a struggle against uncertainty, a struggle against poison. The evidence is everywhere once you begin looking. Consider soaking, across countless cultures, beans, grains, nuts, and seeds are soaked before cooking. The reasons vary. Texture improves, cooking times decrease, flavor changes. But many of these practices also reduce compounds that interfere with digestion or nutrient absorption. Modern science can explain the chemistry. The tradition often existed long before the chemistry was understood. The same pattern appears with fermentation. For thousands of years, human communities have fermented foods using techniques passed through generations. Fermentation improves preservation, alters flavor, and sometimes enhances nutritional value. In certain cases, it also reduces naturally occurring toxins or makes foods easier to digest. Ancient people did not need microscopes to recognize the results. Experience was enough. A method that repeatedly worked survived. A method that failed disappeared. The process resembles a vast experiment conducted across thousands of years and countless communities. Humanity becomes both the researcher and the subject. One of the clearest examples involves cassava, a plant that today feeds hundreds of millions of people. Certain varieties contain compounds capable of releasing cyanide if improperly prepared. Traditional processing methods can dramatically reduce these dangers. The details differ from place to place. The underlying principle remains familiar. Knowledge transforms risk into nourishment. Without that knowledge, the plant becomes hazardous. With it, the plant becomes one of the world's major food resources. The lesson could easily have originated in prehistory. The same relationship appears again and again throughout human food systems. Acorns, beans, various roots and tubers, numerous seeds. Many require preparation techniques that seem simple on the surface, but reflect generations of accumulated understanding. One lesser-known example involves bitterness. Modern consumers often seek sweetness, yet many traditional cuisines include bitter foods. Certain greens, herbs, roots, and beverages retain flavors that some people initially find challenging. Part of this reflects cultural preference. Part may reflect an ancient familiarity with plant chemistry. Human populations have spent so long interacting with chemically defended plants that bitterness itself becomes woven into culinary traditions, not as a warning alone, as an expected part of food. Coffee provides an interesting case. Its bitterness originates partly from compounds that plants evolved as defenses, yet humans transformed those same compounds into one of the most widely consumed beverages on Earth. Again, danger and usefulness occupy neighboring territory. Again, knowledge bridges the gap. Traditional food taboos offer another window into the past. Anthropologists have long debated why societies avoid certain foods. Religious beliefs, social identity, environmental conditions, and historical experiences all play roles. No single explanation fully accounts for every taboo, yet some restrictions appear linked to practical concerns about safety, spoilage, parasites, or preparation requirements. A prohibition may preserve knowledge long after its original context has been forgotten. People continue following the rule. The reason evolves. The behavior remains. This possibility fascinates researchers because it suggests that ancient survival information can persist for centuries or even millennia, not as scientific instructions. As culture, stories provide similar examples. Folktales warning children away from particular plants or locations sometimes contain practical environmental information. Oral traditions preserve memories of droughts, floods, dangerous landscapes, and valuable resources. The exact historical accuracy of individual stories varies widely. Still, many contain kernels of ecological knowledge accumulated through long experience. The boundary between myth and memory is not always clear, and sometimes that ambiguity helps knowledge survive. Human beings remember stories more easily than lists. The deeper one examines traditional food practices, the more visible this pattern becomes. Knowledge does not merely survive. It changes form. A practical lesson becomes a custom. A custom becomes a ritual. A ritual becomes part of identity. The original problem may fade from memory while the solution continues operating quietly in the background. Perhaps the most remarkable legacy appears in our attitudes toward food itself. Modern humans inherit instincts shaped by millions of years of interaction with uncertain resources. Sweetness remains appealing because calories once mattered desperately. Bitterness often triggers caution. Spoilage odors provoke disgust. Novel foods inspire curiosity mixed with hesitation. These reactions are not random. They reflect ancient survival pressures. The world that shaped them may be largely gone, but traces remain embedded in behavior. Even today, people approach unfamiliar foods carefully. They ask questions. They seek recommendations. They watch what others eat. The strategies differ from those of prehistoric foragers, yet the underlying logic feels familiar. Information reduces risk. Shared knowledge increases confidence. Culture continues doing what it has always done, helping humans navigate uncertainty. And uncertainty has never disappeared entirely. Modern societies possess remarkable scientific understanding, but food safety remains a constant concern. New pathogens emerge, contamination events occur, environmental toxins enter food chains. Researchers continue studying compounds whose effects are not yet fully understood. The struggle has changed. It has not ended. What has changed most dramatically is our margin for error. For prehistoric people, a mistake might carry immediate consequences. For many modern individuals, layers of agriculture, regulation, technology, and scientific knowledge provide protection. Those protections are achievements built upon countless generations of observation and adaptation. They did not appear suddenly. They emerge from the accumulated experiences of people who lived much closer to uncertainty than we do. People who learned which plants could be trusted, which routes required preparation, which waters were safest, which traditions preserved life. Their lessons survive in ways both obvious and invisible, and together they form part of a much larger legacy, a legacy explaining how a vulnerable species managed to spread across nearly every environment on Earth, despite beginning in a world where every meal might conceal danger. Seen from a distance, the story appears almost impossible. A species without claws strong enough to dominate predators, without venom, without armor, without the speed of the fastest hunters or the strength of the largest animals. A species entering landscapes filled with toxic plants, dangerous animals, contaminated water, parasites, and unfamiliar environments, and somehow surviving. Not only surviving, expanding, crossing continents, occupying deserts, forests, mountains, coastlines, wetlands, grasslands, and frozen regions. The achievement becomes even more remarkable when viewed through the lens of food. Every environment presents its own menu of risks. Every landscape contains species evolved to resist being eaten. Every unfamiliar resource introduces uncertainty. Yet humans repeatedly find ways to transform uncertainty into opportunity. The answer is not a single invention, not a single adaptation, not a single moment of discovery. It is the cumulative effect of countless small victories, a lesson remembered, a mistake avoided, a technique improved, a warning passed to a child, a preparation method refined across generations. These individual acts rarely attract attention in historical narratives. Empires dominate textbooks. Wars dominate monuments. Kings and rulers dominate chronicles. But none of those stories happen without food. and food itself depends on knowledge. The deeper we look into prehistory, the more clearly this becomes visible. Human survival is not simply a biological achievement. It is an informational achievement. Knowledge becomes humanity's most powerful tool. A sharpened spear matters, fire matters, shelter matters. But all of these depend on learning. Without knowledge, a spear is only wood and stone. Without knowledge, fire becomes dangerous rather than useful. Without knowledge, a landscape remains a collection of threats. Information transforms the environment. The same valley can be deadly to one person and sustaining to another, depending entirely on what each knows. This principle may explain much of humanity's success. People adapt faster than evolution alone would allow because information can spread rapidly. A useful discovery made by one individual can benefit an entire group. A lesson learned in one generation can protect many future generations. Culture becomes a survival technology. Perhaps the most extraordinary aspect of this process is its cumulative nature. No individual understands everything. No community discovers every solution independently. Knowledge grows because people inherit lessons from those who came before. Each generation begins slightly ahead of the last. The advantage compounds over time. A child does not need to rediscover which berries are poisonous. A young hunter does not need to invent every preparation method from scratch. The past remains present through teaching. This accumulation creates something unique, a form of adaptation operating alongside biological evolution but moving at a very different speed. The archaeological record repeatedly hints at this dynamic. Human populations enter unfamiliar ecosystems and eventually learn to thrive. Difficult resources become staples, dangerous environments become manageable, new challenges produce new solutions. The process is never perfect. Mistakes continue, failures occur, communities disappear, knowledge is lost and rediscovered. Yet the broader trajectory remains clear. Humanity becomes increasingly skilled at understanding the natural world. One lesser known but deeply revealing fact is that many foods considered ordinary today would have appeared extraordinary to prehistoric people. Potatoes, grains, beans, nuts, roots, fruits, and countless other staples often require layers of accumulated expertise. Modern consumers encounter the finished result. Prehistoric communities created the pathway. Behind every safe meal stands a history of experimentation. Some of that experimentation was deliberate, some accidental, some successful, some tragic. The evidence remains incomplete, as it always does when examining the distant past. Scholars continue debating details. Archaeologists continue uncovering new clues. Anthropologists continue revising earlier assumptions. No single explanation fully accounts for humanity's relationship with food across every culture and every era. The story is too large for that. Yet certain themes emerge consistently. Observation, memory, cooperation, adaptation. These qualities appear again and again. A poisonous plant becomes edible through processing. A dangerous animal becomes a reliable resource through knowledge. A risky landscape becomes home through familiarity. The pattern never truly changes. People learn, and learning alters survival. This realization carries an important implication. The greatest threat facing early humans was not necessarily poison itself. It was ignorance. Poison exists whether people understand it or not. Knowledge determines the outcome. The same berry can nourish one person and kill another depending on what each knows. The same root can serve as food or toxin. The same water source can sustain life or spread disease. Information creates the difference. Seen in this light, human history becomes a story of reducing uncertainty, not eliminating it, reducing it. Every generation inherits a world slightly less mysterious than the one faced by its ancestors. A few more dangers identified, a few more techniques perfected, a few more lessons preserved. The work is never complete. Nature continues changing. New challenges emerge. But the process continues, and perhaps that is the most remarkable legacy left by those distant ancestors. They transformed experience into memory, memory into tradition, tradition into knowledge, knowledge into survival. The world they inhabited remained filled with hidden dangers, yet they learned enough to endure, enough to adapt, enough to pass their lessons forward, enough to ensure that future generations would not need to begin entirely from the beginning. That inheritance may be invisible, but it surrounds us every day. Every meal prepared safely, every food chosen with confidence, every recipe refined through generations, every warning remembered. Each carries echoes of a much older struggle. A struggle fought in forests, grasslands, river valleys, deserts, and mountains long before history was written. A struggle against a world where every meal carried a question, and where the answer was never guaranteed. The story ends where it began, with a human standing before an uncertain landscape. The forest is quiet. A river moves slowly through the evening light. Wind passes through leaves that have witnessed countless generations come and go. Somewhere beyond the trees, roots wait beneath the soil. Fruits hang from branches. Seeds rest inside protective shells. The world remains what it has always been: abundant, generous, dangerous, and indifferent all at once. For most of our species' existence, survival depended on learning how to read that world. Not perfectly, not completely, just well enough. A poisonous berry became a lesson. A bitter root became an opportunity. A dangerous mistake became a warning carried forward through memory. Over thousands of years, these small pieces accumulated into something far larger than any individual could possess alone. A shared understanding, a collective inheritance. The landscapes that once seemed unknowable gradually became familiar. Forests became maps. Rivers became pathways. Seasons became guides. Knowledge settled into traditions, stories, habits, and daily routines until survival itself became woven into culture. Many of those lessons remain with us, even if we rarely notice them. They survive in recipes handed down through families, in foods prepared a certain way because they always have been, in instincts that encourage caution toward bitterness and spoilage, in customs whose original purpose may have been forgotten long ago. The ancient struggle has not vanished entirely. It has simply become quieter. Today, most people encounter food at the end of a very long chain of knowledge built by countless generations. Hidden behind every safe meal are discoveries made by people whose names will never be known. People who observed, experimented, remembered, taught, and endured. Their victories were rarely dramatic. Most left no monuments, no written records, no lasting recognition. Yet their success surrounds us. As darkness settles over that imagined prehistoric landscape, the final image is not one of danger, but of continuity. A fire burns softly beside a temporary shelter. Food cooks nearby. Children watch. Elders remember. Knowledge passes from one mind to another, as it has for thousands of generations. The world beyond the firelight remains uncertain, but within the circle of shared memory, uncertainty has become a little smaller, and that may be one of the greatest achievements in all of human history.